welcome everyone to our November meeting. Thank you for making the trip out on a cold November evening to be here. Hope you're tucked up nice and cozy wherever you are watching online. The usual bits and bobs at the beginning. First day procedures, see myself or one of the committee. Alan's clear at the back as well. There are no planned fire drills today, but the exits are the obvious ones at the back there and up the staircases. Next slide. So this is our current timetable of coming events. We're still working on our March event to be confirmed. Next month, we are looking at quite an interesting and new topic of sociometeorology. That's an online-only talk, but I can assure you it's a very interactive session. I've seen Helen deliver that before, and that's a really interesting new emerging topic. We've then got the more academic leaning with Dr. Simon Lee coming down from St Andrews to visit us in January, looking at large-scale atmospheric and climate variability. And then we've got our usual early career showcase and 3 excellent early career students visiting us in February. So please come along to those events if and when you can. It's the 24th of February. Well, I'll make that adjustment. Thank you, Jonathan. I'll do my quick advertisement of the benefits of membership of the Royal Meteorological Society. Not only do you get our excellent talks like this, but we've got a whole range of professional accreditation and events and magazines and communications. And it really is broadening the type of events that we host as well just now. So please do take a look online for membership. So anyway, without further ado, we'll move on to our speaker. Very pleased to welcome Michael Bruce, and many thanks for coming down to visit us. This promises to be a really interesting talk. And the pun came to my head. I don't want to say hot topic, but there you go. Michael Bruce has come to join us from Aberdeenshire. He's the Managing Director of Firebreak Services and has been delivering wildfire and prescribed burning training to land managers since 1997. So a real true expert in the field. Michael was on the list of UN FAO forest fire experts for many years and is an active, and was just telling me before the meeting, chair of the Scottish Grampian Wildfire Group and the Scottish Wildfire Forum, which is very active, I believe. Produces wildfire danger assessments for Scotland on behalf of the forum, and I've seen these actively used by the Scottish Fire and Rescue Service to produce public warnings, and excellent they are too. So in this talk, I'll hand over to you in 1 second, Michael. Double check you've got your microphone on, you do. So it's going to be a talk around the recent wildfire data to illustrate and investigate connections with the weather, which is why we're all here. And the relationship between wildfires and weather is fascinating, but not always so direct, with lots of counterintuitive issues along the way. Looking forward to it. So without further ado, over to yourself, Michael. Thank you.
Thank you very much for inviting me.
You just need to share your
Right, and I need to share.
Yep. Share that PowerPoint in the middle. Oh, no, we've shared screen, I think. If you go back to the share. And select that screen, that should be it, yeah. That's us. And then you can go full screen. Fantastic.
Great. Well, yeah, thank you very much for inviting me, and thank you all for coming tonight, and for all of the people online. I hope you can hear me, and if someone can't hear me, please put a chat or a message in chat or something, and I'm sure it'll get sorted. So what do I need to do? No. Which one?
Jonathan?
Now I've got multiple screens to. Yeah. This one?
Screen 2, yes.
No,
Is that?
That's it. Great. Thank you very much. And thank you for the help with the IT. So Michael Bruce, Firebrick Services Limited, and here to talk about wildfires, fuel and weather, a dynamic relationship. So first of all, a little introduction. What is wildfire? I think we need to understand what a wildfire is. We need to understand what the environment for a wildfire is, and we need to understand a little bit about fire behavior. Fuels, that's what we're talking about, and weather, that's definitely what we're talking about. And I'll also talk a little bit about how the Scottish Fire Danger Intelligence System is developing, and then a little summary at the end. What is fire? Fire is a chemical reaction with a combination of fuel, heat, and oxygen. And how it's defined is really if it's anything that's unplanned and that has a negative impact. Fire behavior. And this is the way that a fire reacts to the influences of fuel, weather, and topography, and how it develops. And then we have this thing of the triangle of fuel, weather, and topography. And thinking about how the behaviors of a fire, you have smoldering, slow, and it can burn without flame, creeping, again, relatively slow, running. You hear about fire runs because it's not all at one speed. It grows at different speeds. Torching. You know, you're seeing we're going up the scale here a little bit. Individual tree igniting from bottom to top. And then spotting, when you get embers going ahead of the fire and starting a new fire. And then the one that everyone thinks about, crowning. And that's when the whole forest goes up in flames. So here you have these three main types of wildfire: the ground fire, the surface fire, and the crown fire. 95% of fires are surface fires, burning surface fuels. What we worried about in Scotland in terms of, you know, fires that have a big impact, it's ground fires burning peat. A little bit about what is a fire and how it's measured. So it's this term called fire intensity, which is basically the rate that energy is being released per meter of fire front. And there's a formula for it, and it's been around for quite a long time. But so many actions follow from understanding this concept of fire intensity. So which tools, tactics, and strategies you might use to put out a wildfire. You think about it this in advance, and you think about, well, where do I want to pre-position resources in order to tackle a fire that might happen in a particular region? So fire intensity is a key concept. The next one, which is also important but can get misinterpreted, is the severity of a fire, because this is all about how it impacts on the vegetation and the soil, and you know how the ecology reacts to this disturbance event. Sometimes you get positive outcomes from a disturbance event. You might create the conditions that allow better natural regeneration of pine trees. Other times, if it consumes peat, then obviously you're losing carbon straight to the atmosphere. So there are both positive and negative outcomes from any fire. And then you have you can see this fire triangle there, the basics of heat, oxygen, and fuel that you need to start any fire. But then how does that fire develop and spread? And what sort of intensity is it going to have? So this is where the other three characteristics creating the fire environment come in. The weather, the topography, the slope, things like that. And then what's the fuel? What's happening with the fuel? And then we think about what is fuel. Most people think of it as vegetation normally, but if you're a bit of a fire person, you always think about, you look at stuff that grows and you think, well, it could burn sometime. So let's think about what fuels are gone. We'll start at the bottom. So your ground fuels, these are the things which are low down in the soil, your peat, your roots, your duff, which is your undecomposed matter. Then you come up to the surface, and just on the surface of the soil, you can have litter, you can have moss, little bits of grass, shrubs, little seedlings, dead branches. Those are all your surface fuels. And remember, I was saying that surface fuels and surface fires represent 95% of fires, even in places like Canada. Then moving up again, you can see the tree and you can see the bushes which are linking to the tree, and those are your ladder fuels. But it can also be things like lichen up the stems of a tree, and then the crown. And how closely spaced are the crowns? Because that has an influence on whether or not the crown can go on fire. Then thinking a little bit more about fuel, thinking about the quantity of the fuel, whether it's continuous across a landscape. How big is the fuel? Is it small? Is it big? Because that affects how quickly it might dry. Is the fuel arranged in a way that's all close together, or is it gappy? Because the way that a fire transmits heat to the next piece of fuel is quite often through things like radiation. So if they're far apart, radiation levels drop off quite quickly, and therefore fire intensity and rate of spread, things like that, slow down. Soil type. Well, the soil type affects how dry the fuel might be, and that might depend on where it is on the landscape. And a key thing is, what's the seasonal condition of the fuel? And especially how that leads into the moisture content. Differences between dead fuels and live fuels. Dead fuels are constantly reacting with the atmosphere. And then if you go back to those particle sizes, that is why you have these time lags, these well-known time lags between different sizes of bits of dead vegetation. So your 1 hour fuels can dry really quickly. Small things like grass, leaves, and pine needles. And then slightly bigger things, they'll take a little bit longer to dry out. And then bigger things, large branches and small logs, and then really big things. And indeed, things like peat in the soil take a long time to dry out. Sure.
That response to a
We'll come on to this. We'll come on to this. I'm focusing on fuels at the moment because I have to sort of do it in stages. Okay, one thing that may surprise you is that wildfires in Scotland, the main season is actually in the late winter and early spring period. And you can see that this is from the Scottish Fire Danger Rating Research Project that I was involved in. And you can see that the main fuels which burn are shrublands and peat bogs and some grass. And the main period that we have wildfires, and that's true, very true this year, was in April. And that's what you say is the winter-spring period. So thinking about our fuels in Scotland, you've got grass, you've got heather, and in the springtime, before they start growing again, which is what we call green up, you know, all of these fuels, you can see it in the photograph there, they're all dead fine fuels, less than 6 millimeters, 1 hour fuels, they dry out very quickly. So they only need a little bit of dryness to become what we call available fuel, which is fuel which is available to burn. Thinking about heather, so 92% of our fires are in heather moorland of one type or another, whether it's grassy heather moorland, mossy heather moorland, it's basically heather moorland. And heather moorland represents 50% of the Scottish landscape. So, and it's often places that there are not many people. So people are not thinking about heather moorland, but it is really synonymous with Scotland. And if you think of it in farming terms, you know, 70% of Scotland is in a less favored area, which means it's high altitude, poor soils, and semi-natural vegetation, like heather. And heather, depending on how old it is, has different fuel characteristics. And you can see with the young heather that it's obviously quite short, it's quite dense. There's quite a lot of live material in the sort of length of the heather. And you compare that to the old heather, and you can see that there's more dead material in the old heather. And there's probably a little bit more mossy stuff on the ground as well. So there's a huge difference in the quantity of fuel between those two, just in terms of age. And there's also different characteristics in how quickly they dry. You're thinking about the arrangement of these fuels. And you can see in the background, in the old picture, in the old heather there, you can see a dead tree, which was burned in a fire in 1920. So standing dead wood is good for the ecology. And thinking about things which are a bit more like, blanket bog, which you've got a bit of moorland on top. And you've got a mix. You can see in the photograph, you've got a mix of fuels: heather, grass, moss, litter, and the peat underneath it. You can see some of the peat is a little bit exposed. And that's quite often where a fire can enter an area of peat. And you also see that even though it's short, there's actually quite a lot of dead material in it. And that, as I was saying before, that dead material is reacting with the weather all the time. One thing to note in particular about moss, and we're talking about sphagnum moss, and everyone thinks that sphagnum moss is great. In fire terms, it is mixed. In the winter-spring period, yes, it's fully saturated, 300% moisture content, but in the summer period, it can lose its moisture quite quickly because it can't control its moisture. Mosses can't control their moisture, so they actually react a lot with just the humidity in the air. And the other issue with peat is that once it dries out in a drought, it creates a sort of layer on top of it, and it takes a lot of steady rain, not great big dumps of rain, but just bits of rain, for the water to penetrate and re-wet the peat. This is from a very famous heather moorland ecologist called Professor Charles Gimmingham, who's sadly no longer with us. But I'm pleased to say that his legacy continues in that the inaugural award of the Charles Gimmingham Award was made to a young researcher in Birmingham University, Katie Iverson, at the UK Wildfire Conference in December 2024 at Aberdeen, which was where Charles Gimmingham did his work with Aberdeen University. And here, if we take out the lots of noughts on the vertical column, what you're seeing there is figures of 20 tons per hectare and 40 tons per hectare. And recent research done in the FireRes project in Europe is indicating that you can get extreme wildfire events with as little as 10 tons per hectare of fuel. And what you can see here is that the above ground biomass is growing, and it goes through a period of pioneer, building, mature to degenerate through the time period of about 40 years. But on top of that, you have this accumulation of the moss and litter layer. And so you can end up with an incredible fuel load of up to 40 tons per hectare. And that is very significant. And it's very significant to what happened in Scotland this summer. You've got other fuels in our landscape, bracken, and you can see the seasonal pattern coming in here where it's wintertime, the bracken has died back, it's gone brown. It doesn't take much for all of that fine fuel to dry out and be ready and available to burn. But what you also have with bracken is this huge mat of dead material in the soil surface. And in the Saddleworth Moor fire in 2018, you could see, even though the grass was green, that the fire was progressing through that mat of bracken on the surface. Gorse. This is a picture of a well-known fiery area just outside Aberdeen called the Gramps. And it's an area which always has gorse on it. And I'm afraid people like igniting things in it, and it creates quite spectacular fires on the edge of Aberdeen. And then dropping down, and the ground fuels. This is where your peat comes in. And peat burns, again, there's a relationship with moisture content, but there's also a relationship with the amount of stone in the peat. And as the proportion of stone goes up, then it's less likely to ignite. But see the way that it burns. It creates these caverns underneath the surface of the soil, holding the heat in, and then it just progresses and progresses and progresses and just keeps going. And then forests. You can see a picture of the fire, quite a big fire going through a forest. But the question you've got to ask, is it the trees that are burning? And actually, in this picture, it's not. It's the heather that's burning underneath the trees. And this again happened this summer, and it's happened in other places. Very often, what you find in a forest is that the wind speed drops because of the trees. The relative humidity is about 30% higher than on the open ground. So you'd think that that means that there's no problem, that the fire will go out. And sometimes it does go out when the fire reaches the woodlands. But if you have a creeping fire and a smoldering fire, which gets into the roots, it travels along the roots and it gets a little bit of oxygen along the fine hairs along the roots. And then the fine roots start to burn and it burns back towards the main stem. And you end up with this hole with a tree which might just about be standing, but a little bit of wind, it'll knock it over. So now I'm going to start talking about what you guys probably are a little bit more interested in, which is the weather. And I've broken this into three sort of categories because I think they're all really important. You've got the instant weather that's happening, hourly, in a location. You've got the seasonal pattern, and you've got the relationship between the seasons of the weather and the seasons of the plants. And then you've got the long-term stuff, thinking about the climate. And I actually think it's what's happening in our seasons, which is most relevant to what's happening with the wildfire situation. And we've got to think about how does weather affect how dry vegetation or the fuel is. And part of that is you've got to think about what is the growth stage of the plant. Because when a plant is growing, it's 100% moisture. But when it's dead, totally different picture. And then the other thing is that if you've gone through the cycle of growing, and then you start to get to a long, hot, dry summer, and you get this thing called curing, which is the grasses have seeded, and then they start to die back, and they go brown, and you'll find that in that situation, the grasses need to be 50% dry before you get fire spread. So the residual moisture will contain a fire in the summertime. It's different in the springtime. In the springtime, and this is research done in Sweden, you go from a period when it's very dry, and then you only need 10% of fresh green grass, and it stops the fires. So you've got these differences between the seasons and the way that the fires react with the plants and the plants react with the weather. And why is this important? Why is fuel moisture important? Because fuel moisture affects about 8 different parts of this fire environment, which, it leads to, if fuel moisture is lower, it increases the speed to ignition. If fuel moisture is lower, you get a higher release of energy. If fuel moisture is lower, you get faster fire spread. It just goes on, and fuel moisture is really important. And it affects all of these stages of combustion. Now, first of all, I'm going to draw your attention to the funny faces, because the purpose of the funny faces is to talk about our cultural assumptions about fire. So if I did a little, survey in the room, and I said, when do wildfires happen? I've had this response quite a lot from a lot of people, because the natural reaction is that fires happen in the summertime. Yeah. 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 Okay. So, but when I'm talking to someone in the Mediterranean and I'm trying to explain that we have winter and spring fires, they say, what? And it impacts on a way that an awful lot of academics approach the topic. So it's not just, person in the streets reaction about when do wildfires happen. It actually embeds our whole culture. And this is an issue that I struggle with quite a lot. And you can see it there in the picture. You can see the snow, you can see the dead grass, and that's reacting constantly with the weather. And different things are happening in different seasons. That was the other thing I wanted to try and show. And why? Okay, so I'm going to spend a bit of time on this. In the graph, you can see two periods. The blue-purple line is indicating what's happening in October, and the red line is indicating what's happening in February, March. And this is heather. And what you can see is that normally heather is in this range of about 100% and above, 120% moisture content. But when there's a frost, boom, look at the drop in fuel moisture. And what this means to me is that actually one of the most tricky periods, when fire danger changes fastest, is actually in the winter when we have a frost. So, and people are always surprised, and I see it in the news, that, they get this warning in February. And they think, oh, no, it's climate change. Sorry, it's not. It's normal weather in Scotland, and we have frosts at that time of year. But if I transpose that to Norway, Norway normally in February and March has snow. Why are they seeing more wildfires in that time period? Because they don't have snow anymore. Now, the effect of climate change in the wintertime in Norway is actually to expose these fuels to the frost, and then they dry out. And very often, this is associated with a high-pressure anticyclonic condition with low relative humidity, and there's often easterly airflows. But what is also happening is that we're getting blocking high-pressure systems for longer periods of time. And that's affecting our seasonal developments. And it dries everything out. And in particular, and what this is showing, this graph is showing that red line, is that is live fuel moisture. Let alone dead, that's live fuel moisture. That's being where you're going from 100% down to 40%. We had a wildfire in our locality when I luckily had a research assistant and went out and tested the heather, and it was down at 20% moisture content. Now, these plants should be dead, but heather is a very robust plant, and they weren't dead. They were just not able to control the moisture. And this has been explained to me by someone from America, is that when the soil temperature gets down below about 4 degrees, the roots find it very difficult to take moisture up into the plant. And that means you're still, if it's a bright sunny day, it's still trying to photosynthesize. Even, it's not a huge amount, but it's still trying to draw up moisture, through its xylem and into the plant. And it can't get the water from the roots. Therefore, it dries out quickly. So this is one of the counterintuitive bits why I'm spending a bit more time on it. But it is why some of the highest fire danger periods are happening in late winter and early spring, because you've got these processes. You may have heard it, freeze drying. That's what they do to make things ready for your deep freeze. And you can see this in the different seasons. So I said we've got this cultural assumption that summertime is when, is the high fire danger period. And you can see normally, actually, fuel moisture is at its highest in the summertime, because that's when these plants are full, they're growing, and they're full of moisture because they're growing and sucking up moisture from the soil. Autumn is a transitional month. It's starting to go into senescence, and you can see that the fuel moisture, the live fuel moisture, is starting to drop off. And then you can see in the springtime, that's when it's driest. The Canadians call this the spring dip. And then think about grasses. And I mentioned this thing, you know, that picture of the landscape full of grass, you know, and you're thinking that's just about 50% cured. And you look at the other pictures and that's getting up to 70% cured. So it does need, you need that long-term drought to get the grasses that dry. The first thing though is the thing that the plant's trying to do, which is grow a seed. And once it's grown a seed, then its ability to control the moisture in the rest of the plant starts to diminish. So you've got this constant reaction between the weather and what the plants are trying to do. And you can see this in the seasonal stages of grass. And this is actually an image from an Australian book, but the processes are still the same. You have growth, you have senescence, and you have this residue left over for quite a long time period through the winter, right the way into April and May, which is when you start to get the fresh growth. That's the little green line. What are the weather factors which affect wildfires? Air temperature, yes. The higher the air temperature, the most direct thing is the closest to the ignition point your fuels are. Sunshine. The sun directly heats your fuels. And if it's cloudy, it doesn't heat them so much. Relative humidity, and indeed another one, vapor pressure deficit. I haven't put that up here because it doesn't follow on to the next slide, but vapor pressure deficit is being seen increasingly as being one of the best measures of how drying the conditions are. Wind is the most fickle of these weather factors, changes constantly. Both, you know, the direction and the wind will push a fire in a certain direction. And obviously the wind speed, it will increase the rate of the fire spread. Weather pattern, is it stable or unstable? If you're trying to work out where you're going to allocate firefighters around a fire, you need to have a pretty good idea what direction the wind's coming from, and it can change just like that. So how does wind affect the progress of a fire? Well, it bends the flames so that they become closer to the next door fuels. And in that process, they start the preheating and the pyrolysis of those fuels into fire. The other thing it's doing is it's pushing embers forwards into the next bit of fuel. And wind is one of the things which most affects fire spread. A daily cycle. Now this is an average day. And you think of it, you start off, I'll call it at dawn or pre-dawn at about 5 o'clock in the morning, and air temperature is lowest. It's when you get the dew or the frost. And relative humidity at that point is the highest. And that's when the plants, and especially the dead material in the plants, are absorbing moisture. Air temperature starts to go up, relative humidity conversely starts to go down, and then there's a time lag because the fuels are drying out. So very often the period of maximum fire intensity is mid to late afternoon. So you've got this time lag happening. So it's not immediate, there's a time lag. And then it accumulates over days with this pattern. Solar radiation. There is a relationship, direct relationship between the power of the sun and how hot the fuels get. And you see this on a landscape in the different fuels that you have between a north slope and a south slope. You also have this thing, is it cloudy or is it sunny? And it is quite powerful, just the direct heat from the sun. I was mentioning this thing about wind and why, if you're on the fire line, you need to be constantly aware of what's happening with the wind. Because this is called dead man's corner. If you have a situation where you have a fire progressing with the wind in a certain direction, wind changes, and then what was quite a quiet flank suddenly becomes the head fire. Dangerous, a dangerous situation. And there are lots of things that can cause that. You could have air pressure changes quite high up, pushing air down, and you get different laminar flows. You get contouring winds, which suddenly flick from one side to the other of a hill. You know, that's why I say wind is fickle. Now we're going to start talking about fire danger rating systems, because forecasting and trying to help people understand what's going to happen in the near term is really important. But there are some principles behind it. You try and make it work over a broad area for general purpose. You don't try and become too detailed about it. The weather forecasts that are available, I call them Rolls Royces. You know, they are really high quality. Where we're at in terms of fire danger systems, we're a little bit in the cart and horse stage, just to give an analogy. So, but other things about this, you have to try and define a period of time, and it's easier to define the start of a period than it is to know where the end of the period is going to happen, because it changes as the weather changes. And on the wildfire danger assessments that I write, I always have a standard clause saying, and when it rains, the fire danger will drop. So I'm trying to get around that thing of defining a time period by saying, actually, just wait until it rains. And that's when you're going to see the change in fire danger. And the messaging is so important, because you've got both a technical audience and a public audience, and probably other audiences too. But that means that you sometimes need to have different messaging to these different groups of people. And we do that in the system that we've got in Scotland. And what's the purpose of a fire danger rating system? It's an assessment of the fixed and variable factors of the fire environment, which determine ease of ignition, rate of spread, how difficult it is to control. And that's not just one fire, but when you get multiple fires, when you get fires which smolder for weeks, and you have a drawdown of resources. So this thing of difficulty of control, it's not just the immediate flames, it's the whole context that you're operating in. And then fire severity, the impact of the fire. The favorite, the most widely used fire danger rating system in the world, the Canadian Fire Weather Index system. I love it and I hate it. And I'll explain why. Okay, so first of all, I think it's a misnomer. It's not a fire weather system, because it was built, it's a very empirical system. It was built on thousands of fuel moisture and fire experiments, from which they developed fire behavior models. And then they wanted to apply these fire behavior models across Canada, and they worked out how they could do it with 4 simple weather inputs. So the reason it's called Fire Weather Index is because the inputs to this system are weather. You have 3 fuel moisture codes. You have 2 sort of fire behavior bits, 3 fire behavior bits to include the ultimate aim of the Fire Weather Index. And you can see that the fine fuel moisture is determined by temperature, relative humidity, wind, and rain. The initial spread index is determined by the fine fuel moisture code with an extra factor for wind. The Duff moisture code is more simple and long-term. It is temperature, relative humidity, and rain. And then the drought code, even more long-term, is just temperature and rain. And then they have a fuel component. The build-up index is trying to give an indication of how much fuel is involved. So you combine the rate of spread with the fuel to create the fire weather index. And the fire weather index is supposed to be an indirect representation of fire intensity, going back to that fire behavior thing that I started off with. So how do the Canadians use this thing? They create these simple colors and call them low, moderate, high, very high, and extreme to represent in terms of fire danger classes. And they have descriptors for it. And if we look at the very high, it says high intensity fire with partial to full crown involvement, head fire conditions beyond the ability of ground crews, air attack with fire retardant required to effectively attack the fire's head. Then greater than 4,000 kilowatt per meter fire line, fast spreading, high intensity crown fire, very difficult to control, suppression activities limited to flanks with only indirect actions possible against the fire's head. So what they're doing with this thing is they are giving firefighters advance notice of the type of fire behavior they're likely to encounter with a fire. And they have them split into these FDR, fire danger rating, FWI classes. And what they don't show, but I managed to know it because I've asked various people and found it out, is that what they're actually indicating is bands of fire intensity, kilowatts per meter fire line. Now, you see 4,000 there as being extreme. Our heather fires, a recorded one from this autumn with fire intensity of 15,600 kilowatt per meter fire line. So shrub fires can create these very high fire intensities, and a heather fire is a shrub fire. And these are two of my favorite people. It's Charles Wagner, who I never met, and Marty Alexander, who I have met, has been a friend for 40 years. And they are very realistic. They created this incredible system out of maths. They didn't really have computers when they created it. It was pure maths that they used. And what they're trying to achieve is make an index such that any given value will represent the same fire behavior no matter what weather history leads to it. Now, you guys know how complicated weather is, and I've indicated how complicated plants are. So this is a very stiff test. The trouble is one very quickly outruns the available practical knowledge. And the other thing that's really struck me, the way those original Canadian researchers present their work, is they always start with their assumptions. And they're very clear about what is in the model and what is not in the model. And that's really important. Because I find very often when researchers start using the fire weather index, is they don't understand the assumptions behind it. They don't understand how empirical it is, just suited to the Canadian ecology. And when you then transpose it into another ecology, you've got to be really careful you get your adaptation right. And we're only just at the stage of starting to adapt the Canadian system to our context here. And Marty says it's also very difficult to portray all aspects of fire danger in a single number. One number can't be expected to cover the full range of fire management needs. Wisdom. Because, and it still happens to me, I still make mistakes. I have been, writing wildfire danger assessments since 2014. I've now got 11 years of experience and I still make mistakes because this year even, each context is different. So you've got to be I think you have to be careful whether or not you're making this false negative or false positive prediction. So I said I love it and I hate it because some bits of the system work and other bits don't. The fine field moisture code, we've managed to get a way to work it. The Duff moisture code works some times of year. The drought code works at other times of year, but not in other periods. And if you think that they're linking it all straight to the fire weather index, which is this main representation of fire intensity, well, if you think of it, our main fire season is in the winter time and in the springtime, and the soil is saturated. And yet here we're trying to say that, the deeper soil is having an influence on fire weather, on the fire weather index. It doesn't. It obviously doesn't. And that's why I'm saying you need to know how the system is built up. You need to know the assumptions behind it. And the other key one, is that there's no shrub fuel model in it because they don't have shrub fuels. We've got some now, and they're trying to adapt it to some shrubs in Nova Scotia, but it's struggling because it was never designed to do that. Scottish government put some money forward in 2006, 2008, and my role in this was I was chair of the steering committee, and it was work done in Edinburgh University by Colin Legg and Matt Davis, and then subsequently by Roger Grow-Andres. And we found some interesting things. Fire intensity of heather fires was unrelated to the fire weather index. So the key thing this system is designed to produce didn't work. But we did find a correlation between the moss and litter layer and the fine field moisture code. And subsequently, we also found one with the initial spread index, because that's built on the fine field moisture code. And we found that we could also get some information about potential peat ignition, although this year, problems with that. So I've showed you these images before, but you can see there's no shrub layer moisture index. And you can see the bits of the soil that each of those soil moisture codes are trying to collect information on. And then you think about our heather moorland, and you think about the moss and litter component, which is what the fine field moisture code is giving us some information about. And you think about the shrub layer, which it's not really giving us information about. But what we have managed to do, and this is part of the Scottish Fire Danger Rating Research Project a couple of years ago, is we're finding these relationships and quite clear relationships. And Marty Alexander from Canada, he said to me when I described heather fires to him, he said, yeah, they're like mini crown fires with an off-on switch. And you can see that off-on switch quite clearly in these plots. So the first one shows you that, you know, when fine field moisture code gets above about 75, 80, you get this wildfires happening in Scotland. And then it's even clearer when you combine the fine field moisture code and the initial spread index. You get this very clear clump of when our wildfires occur. So we looked in that 2006-2008 study, we looked at previous data of wildfires in Scotland, and we found this relationship. And you can see it quite clearly that the number of wildfires are happening when the fine field moisture code climbs above about 75. Then the Scottish Fire Danger Rating Research Project, that's on the other side, we honed in a little bit more. You know, we had more data from the European Forest Fire Information Service, and we were able to, and this is what we use now. So how do we use it? From that information, developed a lookup table, which is a combination along the vertical side of the fine field moisture code, which I think is reasonably accurate on a daily basis, and then wind. And we have pretty good forecasts of wind. So that is combined, and you just plot it across, and then you work out all of that stuff based on the initial spread index, which is how those fire danger classes are split out. And then there's a little thing there, 20 kilometers plus of wind, you have this very steep rise in fire danger, which also concurs with traditional knowledge. So you'll see it in older versions of the Muirburn Code, where traditional knowledge was collected. Watch out when the wind speed gets above 20 kilometers per hour, because then the potential for wildfires is much higher. What's the process that I go through each time I produce a wildfire danger assessment? First of all, I think about which is the fuel type. Don't think about the weather at that point. I think, what fuel type am I thinking about? I think about what stage are we at through the season? So what's the condition of the fuel types in that season? And is it normal or is it abnormal? Are we ahead or are we behind? I get the various fire indices from the European Forest Fire Information Service, and I also get weather forecast information. And I love things like deep dive. You know, if I've got anyone from the Met Office online, you know, I love those longer term products. They really help me. And then I prepare a wildfire danger assessment, and I write the interpretation, which has a section on the seasonal condition of the fuel. I share that assessment with the Scottish Fire and Rescue Service wildlife tactical advisor who's on duty. We agree it, and then it's issued. And the one that most people will see is the public one, which is issued by the Scottish Fire and Rescue Service. And then there's a slightly more technical one, which goes to things like all the utility companies. It goes to the agencies. It goes to a lot of land managers, and all the land management trade associations like Scottish Lands and Estates, Scottish Gamekeepers Association, National Farmers Union for Scotland. You know, it goes to all of them. I always ask, what was it like? Was it about right? Was I about right? Have I got a false negative? Have I got a false positive? I'm always trying to think, is it right? Because each one is different. And I don't know if any of you have seen these little maps of Scotland with colours on them, but they're generated by the European Forest Fire Information Service. The trouble is, their fire danger classes are based on Mediterranean conditions. And we're in a slightly different situation, but you know, the system we've got at the moment is we use some of the colours and we give them a different descriptor, a different interpretation. And what do we do with this information? Well, people go out and they put out high fire risk signs on a locality basis. They'll increase how much patrolling they do of campsites or places where we know people have barbecues. So there's quite a lot of preparedness work goes on the back of these assessments. Now I'm going to go back to Canada. And in this, what you can see is that different indices are more important in the different seasons. So in the springtime, it's initial spread index. But as we know, initial spread index is built on the fine field moisture code. When you get to early summer, it's driven by, if you have a sharp drought in early summer, it's driven by the Duff moisture code. In late summer, long-term drought, it's the drought code which becomes more important. And then the season end, it gets a bit confused. And that's what happened this autumn. And I'm just going to run through some examples of how this system is giving us some really good information at different times of year. So I don't know how many of you remember the beasts from the east. Blizzards, gales, pile-ups on motorways. And I thought, we've got this relationship with frost. I better check. So I did check. And I found that there was a little corner of Scotland based around the Isle of Skye, which actually had a different situation. And so I wrote my wildfire danger assessment. I sent it into the fire service, and it caused consternation because they were gearing up to deal with lots of traffic problems. And lo and behold, I was saying there was fire danger. So there was a bit of hilarity, which soon stopped when, bang, 4 big wildfires on the island of Skye. Paul's Hill wildfire, very close. In actual fact, some of this was burnt again this summer in the Darver part of the Darver-Carbridge wildfire. I predicted it. Looking at the initial spread index, you can see there's an awful lot of red in northeast Scotland. And that fire went straight through the wind farm. Did quite a lot of damage. I'm going to get the pronunciation of this one wrong, but I think it's something like Llantysilio in Wales. And here you're looking at a dry summer, mid to late July, and the difference between one day and the next. And what you're seeing, I may have to put my glasses on. Sorry about this is so small, but I'm picked up on previous slides, so I'll read it out. So on the 18th, the fine field moisture code was 76.5, and the drought code was 392. So the drought code is indicating that you could have smouldering, but the fine field moisture code is below 80. So it's not that severe. Initial spread index on the 18th is 1.4, which is low. There was a fire ignited. fire service went, they put it out, they thought it was out, so they left. The next day, when the fine fuel moisture code had jumped to 84.4, so that's well over 80. The Duff moisture code had jumped 3 points to 27, and the drought code had jumped 8 points to nearly 400. That's in one day. What happened? It rekindled. They were back again, back again, back again. And you can see the value if you have a system like this to give you predictions of potential fire behavior, that it helps on the allocation of resources. The big one, this summer, Darver-Carbridge wildfire. It potentially started on the 20th of June, because that was when the first bit of fire was recorded. And it was handed back to one of the landowners or land managers on the 14th of July. So the fire service, they have a formal process of handing a site back into the control of the landowner. So the Darver-Carbridge wildfire, probably Scotland's largest ever, 9,800 hectares, and it burnt all fuel types. It burnt managed moorland, it burnt peatland, it burnt mature woodland, it burnt young woodland, it burnt native woodlands. And it was in the native woodlands, the sort of things that people might have called a rewilded place, that fire intensity, rate of spread, difficulty of control was highest. And they were able to get on top of the fire a little bit where it was managed moorland. And the amount of damage to the peat layer was less on the managed moorland than it was in the other areas, either peatland restoration areas or in particular in the woodland areas. Why? Because the fire got in around the roots and burnt and smoldered for weeks. Thank you very much, Royal Meteorological Society and Jonathan, for the other picture of the synoptic chart, because there were some very unusual weather conditions. You know, there's been complaints the helicopters were not available. Actually, they probably couldn't fly because the wind was so high. In some places, was it 60 kilometers an hour? You know, people have said it's even higher than that. So that wind, that fire was a combination of a fuel-driven fire and a wind-driven fire and an aspect. You had all of the factors in alignment to create these incredible fire runs. What do those fire runs create? Extreme fire behavior. So you had 20-meter plus flame lengths. You had rate of spread, I've seen and some calculated in some places, of 2 kilometers an hour. You had spotting over 750 meters, but regularly in the 40 to 100 meter band. It jumped fire breaks, you know, you name it, it did it. And this is it's either at or very close to being defined as an extreme wildfire event. And in the European context, that is what they're becoming increasingly worried about. Because when you get to extreme wildfire events, it's no longer just a wildfire, it's a natural disaster. The communities around this fire are now extremely frightened. They had smoke, they had burning embers, they had, you know, a number of them had to be evacuated. Roads were closed. You know, the impact was tremendous. The biggest impacts have been on the forestry areas, with damage to potentially 1,000 hectares of woodland. 1,000 hectares. What's our planting target every year? 14,000 hectares. So you can see that we don't just have to look at what we're planting to think about what we're going to try and do that's beneficial in terms of climate. We also have to avoid losses. And one of the areas that losses occur is through wildfires. Biggest loss was to a wind farm. And again, we're all trying to go green. There's been a wind farm which was de-energized on the date of the fire and is still not re-energized. Think about what that means in terms of lost revenue, apart from anything else. So you had this wind-driven fire, extremely dangerous for the firefighters involved, which included quite a lot of estate staff. And it was the estate staff who were very much on the front line because they've got all-terrain vehicles which they use for mure burn. But that's been reported extensively elsewhere. Other recent research is indicating the impact of heat waves. So I've gone through and I've described how dead fuel relates to weather quite a lot, and it's quite a, it depends how big the thing is, and then it's quite a direct relationship. I've indicated that for live fuel, it's the phenological condition of the plants, the seasonal condition of the plants. And then for the organic layer, if you think of it, are you in a water shedding part of a catchment or a water receiving part of a catchment? And indeed, it's also what is this underlying soil type. I've mentioned, this thing of these anticyclonic blocked high pressure systems, which first of all create drought. And then, as you can see, it builds up and it builds up and it builds up. You then get your heat wave. And what happens, what the researchers have found, this is people in part of the United Kingdom Fire Danger Rating Research Project, in particular Birmingham University, what they've found is that fuel moisture collapses when you have a heat wave. In plant terms, was it hysteresis? I think it's something like that. Anyway, so basically it stops, the plants stop functioning and they start dying. And all these three main fuel components become controlled directly by the weather. Now moving on into what is happening in Europe and other parts of the world, it used to be that we used to get about 3 around the world of these things, these pyrocumulus clouds, which create beyond extreme fire behavior. So it starts off with this buildup of convection, heat by convection, which goes up into a cloud. And then as the cloud grows and grows into the atmosphere, it cools down, and then the air starts to drop around the outside of the cloud. And sometimes you might get rain on the outside of the cloud, but often you don't. And you can see in the other picture, what you also get in these storm events is you get dry lightning, and that is starting up new fires. And then the other thing is, when that cloud system collapses, you get rapid spread in multiple different directions. Incredibly dangerous situation, and this is a natural disaster waiting to happen. What the researchers are indicating is that one of the few ways that you can try and prevent that collapse is by investing in rural land management, by investing in managing the fuel load, by breaking up the fuel load so that it doesn't get this huge amount of fuel to burn and build up, and then potentially then create these very dangerous situations. And we're not far away from it. So if you look at some of the pictures of the Saddleworth Moor, huge mushroom cloud above the fire site, that is the start of your pyrocumulonimbus system starting up. And this is where a fire, it's not where the weather is impacting on fire behavior, it's where the fire is creating its own weather. And when one of these things happen, it's like, in terms of energy, it's like an atomic bomb going off. This is where we're heading. And this is what they're calling 7th generation wildfires. And the only way that you can do things to start to prevent these, as I'm just going to repeat myself, is by doing active land management. So I'm getting towards my close. And I'm going to summarize. Land use change is increasing fuel loads at scale across our landscapes in Scotland. Most wildfires in Scotland happen in the early spring period, and it's controlled by the phenological condition of the plant, with fire behavior on the day controlled by wind, aspect, and slope. And when those 3 factors are in alignment, that's when you get fire runs. Yes, with climate change, the weather will have an increasing influence on spring fires, in particular, if it raises temperature, lowers relative humidity. But in particular, we're going to see more of these summer and autumn fires. And that also means we're going to see more smoldering of the peat, more carbon emissions. And the carbon emissions from the Darver Carbridge wildfire, 500,000 tons. Yeah, it's immense. One fire, 3 days. That's all it took. So this is where I say thank you. And I say thank you to an awful lot of people, because I'm on a learning journey. I still make mistakes, and I like talking to people about this topic. It's fascinating. It's difficult. It's frustrating. And you need a group, and the group is very international. The people who talk about fire and fire management is a very international group. I think it's probably quite a lot like people who talk about the weather. It's very international. And in particular, and now sadly we are without Charles Gimmingham, but I still read his book from the 1970s. I still read his book. Matt Davis and Colin Legg here from Edinburgh University, they worked together. And Matt Davis, on the back of that research we did in 2006 to 2008, has produced paper after paper after paper. Look him up. A friend, Wendy Anderson, she is the statistician that all of the fire researchers go to talk to. Marty Alexander, I've introduced him already. Johann Goldammer, he runs a Global Fire Monitoring Center in Freiburg in Germany. And then we have the young researchers who are coming forward. There's others from the United Kingdom Fire Danger Rating Research Project. And they're all at the stage of producing papers, and it's going to be very interesting in the next 6 months to 12 months, the work that as they are able to publish their work. Nature Scott have been helpful, providing funding very often and long-term support. Continuing support from Jesus San Miguel from the European Forest Fire Information System. The Pau Costa Foundation are very much, Mark Castelnu is focusing on this pyrocumulus things. And then yourselves, because thank you for inviting me. Thank you for listening to me. And thank you for the contribution of the slides, so I could explain some of what was happening at the Darver Carbridge wildfire this summer. So thank you very much.
Thank you, Michael. That was an excellent talk and really clearly explained. Thank you. It was quite enthralling. We'll have a few questions and answers. I suspect there'll be a few questions in the audience and online as well. Do we need to do anything to bring that up, Alan? You can't. Okay. I'll start very briefly. I always pinch the first question. You explained very clearly around the kind of evolution of the fire danger assessment and modeling it. It's a kind of simple question to ask, perhaps harder to answer. If you had a good amount of resource and so forth, where would you focus to continue improving the fire danger assessment? Is it observations, modeling, or just the pure science?
Two areas. One area would be to improve our fuel moisture models. And obviously there's a weather with fuel moisture. But the other really important one is we need to improve our heather fire behavior or heather moorland fire behavior models. Because at the moment we are using international models, and we have got some peculiar characteristics. In particular, and this is what happened in the Darver Carbridge wildfire, from the gamekeepers who I've talked to, sat down and talked with a lot of them. And what they experienced was not just a surface fire that was burning the heather, but that undecomposed layer at the top of the peat, indeed some of the top of the peat, was contributing to fire behavior. So you had the flaming lengths, and then you had that charring and glowing bit behind it, which was 40 meters long. 40 meters long. So you could have had 8 to 10 meters of flame length in the front, which is extreme fire behavior. And then on top of that, you had this whoomph. And that's what made that fire so difficult to put out. So it was a contribution of the moss and litter layer on top of the surface fire. Mm. And that combination we haven't worked out yet.
Okay. Fascinating stuff. Any questions in the audience? Okay.
Summer of 1976 was similar to this. I was working down south in agricultural meteorology, and there were summer fires. Were there summer fires in Scotland?
Yes.
Similar to this,
Yes.
what we got at Dava?
Yeah, near the Slocht
Yeah.
on the A9. If you go the sort of Granton-on-Spey A9 junction at the Slocht, near the Slocht, and you look at the peat bog just beyond it, you'll see that that peat bog still hasn't recovered from the fire that happened in 1976, not fully. Because what happens when the fire it goes over a peat bog is it creates a crust on the top of the peat, which is impermeable, impervious, nothing wants to grow on it. And I think it's also slightly toxic. So it takes a long time for peat bogs to recover. So if we're going to protect our peat bogs, we need to think about how we're going to cope with wildfires.
I was just wondering what the primary source of ignition is for these fires. Is it people with barbecues, or is it natural? And the pyrocumulonimbus effect, are we seeing that happening in Scotland? I know it's big in Canada and the US, but are we seeing the effects of that in Scotland?
It's a particular set of circumstances which are quite rare that support a pyrocumulus thing. But to give you an indication, a few decades ago, there were about 3 of them in the world. I think last year there was 140. It is what fire managers and fire researchers are most worried about. And then the first part of your question.
Yeah, sorry, how the fires are starting. Is it usually man?
The vast majority of them are accidental in various forms.
Thanks, really interesting talk. Is it? I would say so. Heather Moorland is a very sort of artificial landscape that we've created over the last few hundred years, and I think you commented as well that wilded land was part of the worst affected during this Dava Bridge fire as well. So. And you also said that land management is crucial to sort of controlling the fire. So I'm just wondering, have we essentially created a landscape of heather moorland that is very fire prone, and it's going to be very difficult to re-engineer that into a landscape that is less fire prone? But we want to do that to sort of sequester more carbon and so on. So I'm just wondering, sort of, are we in a sort of almost impossible situation, or can we move to a situation that is a more beneficial in terms of storing carbon and for wildlife and so on? Or are we kind of stuck with a rather difficult land management situation that is very difficult to actually change?
Okay, there's about 4 or 5 questions.
Sorry.
That. And I'm gonna. Heather has been with us for thousands of years. Man has been in this environment in Scotland for thousands of years. Man has been using fire in this environment for thousands of years. The charcoal records are there. Man has been part of this ecology for thousands of years, since the last ice age, but virtually. So is man unnatural in this environment? I don't think so. You have got some researchers, in particular I'm thinking about James Fenton, who has indicated that the forest in Scotland has waxed and waned, depending on the climate. And there have been periods when it's been wetter and colder, and the forest has retreated. So it's not all one direction. The other thing is I showed the picture of what is actually a native woodland. Some would consider it a rewilded landscape, where the fire was burning actively in the heather underneath the trees. And, you know, heather and trees, they are together in Scotland. They're both part of our natural environment. So it's not one or the other. They're both part of the natural environment. And I can take you to areas which have got birch trees, a broadleaf, because everyone says, okay, if you don't want fire, plant broadleaves. There's plenty of heather under those birch trees to burn. And then if you think of heather moorland in more technical sense, and you think of it in terms of fuel quantity, there's a direct relationship between fuel quantity and fire intensity. As fuel load doubles, rate of spread doubles, and fire intensity quadruples. Byram, 1959. I showed him because he was the originator of the fire intensity calculations and model. So yes, we are developing high fuel loads on a landscape scale with the potential to create landscape scale high intensity wildfires. I gave a presentation at the UK Wildfire Conference, December last year, indicating that we were in a situation where we could get multiple wildfires at the same time, which were beyond our ability to control. And I'm very sad to report we had the Darva Carbridge wildfires this summer. So what I'm saying is that we are in this situation now. Land managers are having active discussions. Agencies are having active discussions. What can we do? Yeah, we know that we want to try and have more vegetation, more carbon embedded in our landscapes. But we also know that there is the potential for these wildfires to occur, and in 3 days you can lose 500,000 tons of carbon. So you look at international best practice and you see how other countries who are further along this trend than we are at the moment, and you try and adapt what they suggest to our situations. And I've been involved in discussing this stuff, some of it since 2006. And the Americans, for example, have got a process of strategic fire planning, which indicate you have a primary land use objective, and fire management is a risk management secondary land use task. Okay? So you are still trying to go in that direction, but you have to do various things to mitigate, in a risk management sense, the potential for landscape high intensity fires that you can't control. And that involves things like fire breaks, and you create fire breaks either through prescribed burning, by grazing, or by cutting. Yeah, so the three main techniques. And if you think of them, those are all the types of things that land managers do. So to my mind, we should be thinking about how can we adjust some of the funding regimes, the grant schemes, to include wildfire prevention activities. And we're going to have to change at pace, because the fuel loads that we've got, the weather that we're seeing are creating fire behaviors already that we're finding incredibly difficult to manage. So we need to persuade our politicians, and there was a debate in Parliament last week. They are connected, and this is really, I'm finding it really, we're in quite a potentially good period to actually create strategies that can start to help us manage the land and include fire risk management in how we manage the land. Does that answer your question?
Yes, no, thanks a lot. I suppose, and I think you did sort of say this, but specifically the land management that we need, so you think it's kind of fire breaks and just thinking about it more?
No, it's not just thinking about it more. We're going to have to invest in firefighting equipment. We're going to have to invest in the development of rural fire management skills. We're going to have to invest in a whole range of preparedness and prevention measures. There's a whole suite of activities that we're going to have to start doing.
Okay. Yeah, I was going to say, I always like to involve online. I'm going to read it out. We'll just take a quick one online.
Okay, well, I've got a question online, and I've got a quick question. So I'm just curious to know how much carbon, I mean, I missed it, how much carbon, say, is emitted from the Darva Carbridge wildfire.
I mean, the thing is, they haven't worked it all out yet.
Okay.
So the initial one was about 500,000 tons.
Right.
And just immense.
And the question we've
But
got
that doesn't count for all the forest losses, all the peatland losses. So it's going to be bigger than that.
and there's a question online from Claire, and our question is, would there be any benefit in putting high fire risk warnings into weather apps to raise public awareness? Despite the distribution of information to landowners and managers, the general public are often not aware of periods of high fire risk.
We are discussing that at the Scottish Wildfire Forum level. The Scottish Wildfire Forum have got a communication strategy which involves all of the agencies. There is a Highland weather forecaster who puts them out. So it's you know, individuals are doing it already. I'm not sure. I couldn't say if you know, if you wanted the BBC or people like that to put it out in weather forecasts. I couldn't say. I don't know if what we do is at the quality that they need. As I remember, I said that weather forecasting is, you know, it's Rolls Royce now, and we're at the cart and horse stage.
Thank you again, Michael. Thanks for fielding our questions so eloquently. Thanks again, everyone, for coming. We'll wrap it up there just for the interest of time, but I think we could have talked even longer than we did. But good to see you all. We'll see you online in December and then hopefully in person again in January. But once again, please thank our speaker, Michael Bruce.
Thank you.
Thank you.